This is a short video where I will review how to calculate the process volumes for a wastewater treatment plant for the removal of nitrogen. So I'm going to follow the procedure that is given here for dimensioning of such a plant. First thing is to figure out what is the load of the plant and what are the outlet requirements. In this case, I've specified some volume, some inlet loads here, mass of organic matter in 85 percentile and nitrogen as well. Outlet nitrogen total is normally controlled as a transport standard, and there's typically also an associated requirement to the ammonia that is controlled as a conditional standard, so as an 85 percentile. So really my design criteria should be based on that nitrification should be achieved all year round. Hence, I will choose the organic load as an 85 percentile for the design of my nitrification reactor based on the sludge age. So first thing is that I have to figure out what sludge age do I need according to the design temperature here, the lowest winter temperature that I've got. So my aerobic sludge age has to be bigger than what I can see on a curve like this. Going in with my design temperature and saying, well, I've got to have something like at least 16, 17 days. So if I design by at least 16 days of aerobic sludge age, and using a load which is more than the average, then I'll be able to achieve nitrification also in the wintertime with that aerobic volume. Second thing or next thing would be to estimate a yield factor, and for that I can use a curve like this. So some heuristic, some relationship between yield factor and FM ratio, and I know that for nitrifying plants my FM ratio is going to be very low in the region of 0.05 to 0.07. According to this scheme, that gives me a rate of yield constant around 0.7 to 0.8. I will be a little bit more conservative because I think these data does not really match all the data that I see. Sometimes I get indications of a higher yield, so in this case I will choose a yield constant of 0.85 kilogram sludge per kilogram BOD, equivalent to an FM ratio of less than 0.07 kilogram BOD per kilogram biosludge per day. That can be checked later. So now I've got to calculate the mass of sludge that I produce per day in this 85 percentile situation. So that is the yield constant times the mass of BOD at the inlet. So 0.85 kilogram sludge per kilogram BOD times the design load here. I take 1000 kilogram BOD per day, and that gives me a sludge production of 850 kilogram biosludge per day. So most of this I'll take out here, but a part of it will be removed with the purified wastewater also. Now, since I now know the sludge age, I know my daily sludge production, that tells me my aerobic sludge age, that allows me to calculate the mass of sludge in my aerobic reactor. So the nitrifying volume times the concentration of solids there equals the aerobic sludge age times the daily sludge production. So 16 days times 850 kilograms suspended solids per day. That gives me my aerobic sludge mass, 13,600 kilogram of suspended solids I need in my aerobic process tank. I now choose XA, in this case 5 kilogram suspended solids per cubic meter. I need really to be careful here because XA not only determines the volume here and is important for the size of this part of the plant, but it very much has an impact on the clarifier, on how things will behave here. So it's important to make sure that the clarifier works with this concentration here. That allows me to calculate the aerobic volume simply by taking my sludge mass and divide it by the concentration. And this concentration is something that I control by the amount of sludge I take out of the system. So I can constantly, as a plant manager, go and measure the concentration here, and if it's too low, I simply stop outtake of excess sludge for a day or two, and if I've got too much, I've got to increase my outtake. So this gives me a value of volume of 2700 cubic meter. 2720. So far so good. I should just check on the nitrification rate. Is this sufficient? Because my volume here is calculated based on the organic matter load. And now I have ensured that my sludge age facilitate the retention and growth of the nitrifiers. So they're there. But can they deal with the amount of nitrogen that comes in? That I have not looked at. And that I can take a look at just by looking at the required rate, which will be the mass of nitrogen that needs to be nitrified, divided by the mass of sludge that I have. And now I've got to get this value calculated. So the mass of nitrogen that needs to be nitrified, that's the mass of nitrogen at the inlet minus the mass of nitrogen in the sludge I produce, because the sludge I take out here includes nitrogen in a reduced form so that I do not have to nitrify. So again, looking at the 85 percentile situation, I know my daily sludge production is 850 kilogram suspended solids per day. Out of that, 8% is nitrogen. That's the approximate concentration of nitrogen in biomass. So that tells me that I can remove with the sludge actually 68 kilogram per day of nitrogen. So almost 1/3 of the nitrogen in the inlet I remove with the excess sludge. And I need to remove 142 kilogram of nitrogen per day by nitrification, or I need to nitrify this much. So the rate again will then be these 142 kilogram of nitrogen per day divided by my sludge mass. That was 13,600 kilogram in the aerobic tank, and that gives me 0.01 kilogram per day, or 10 grams of nitrogen per kilogram SS per day. I would like to look at that for the peak hour situation, because nitrogen in the inlet is going to fluctuate a little bit over the day. So I'm not going to just look at a daily average, but I'm actually here going to say, well, nitrification is so important to maintain at any point of time because my outlet is controlled as an 85 percentile and I need to have a very low value. So I'm going to be a little on the safe side here and say, well, my rate, hourly rate, I will take the 10 gram nitrogen per kilogram SS per day and divide by 14 hours per day. So not by 24, but by a value that corresponds to approximate ratio between peak load and average load in a dry weather situation for an urban area of this size. So not 24 hours, but 14 hours, and doing so, I get a rate of 0.75 grams of nitrogen per kilogram SS per hour. And that I have to relate to, and I have to see, well, is that reasonable to expect this? And I can go in and see, well, activated sludge from urban wastewater treatment plants with the composition of the sludge with nitrifiers and heterotrophs, I typically get around 1.5 to 2 gram nitrogen per kilogram VSS per hour as a rate. So per kilogram SS, it's going to be slightly smaller, but still twice as big as the one I need. So I have no problem achieving my nitrification. It's going to be able to, the workers at the plant are going to follow the influx of raw materials and is able to nitrify the ammonia coming in at any given point of time. So far, so good. Then I've got to look at my mass of nitrogen for the denitrification, because now I'm gonna look at that size of the plant. So the mass of nitrogen that I have to denitrify every day is the mass of nitrogen that I have nitrified minus the mass of nitrogen that I'm allowed to have as nitrate in the outlet. Because I'm allowed to lose some nitrate in, I don't have to denitrify all of my nitrate. I can see I have an allowable total quantity of 8 milligram per liter of nitrogen in the outlet. I have to leave space for some nitrogen as found in the suspended solids. 8% of this, maybe my clarifier works a little better than the absolute maximum here, so in average maybe 20 milligram per liter, 8% of that will be 1.6 milligram of nitrogen. So let me reduce this number with 2 milligram, then I have room for suspended solids nitrogen. So I will say I'll take the 85 percentile flow here to be a little bit on the safe side, and then 6 milligram nitrogen per cubic meter as nitrate in the outlet, and I'll subtract that from the 142 kilogram N per day that I have nitrified, and I will get a value of, so I have 20 kilogram actually that I can lose with the outlet, and the remaining 122 kilogram of nitrogen per day I need to denitrify. Next thing is to look at the denitrification rate that I could expect to have. That's temperature and process design, organic matter related. So I need to look for these relationships between temperature and type of carbon source for the denitrification. And let's say here that I've got a summer average temperature in this plant for typically Denmark around 12-14 degrees. Using raw carbon wastewater I get roughly maybe a little less than 1, so let's say 0.9 gram of nitrogen per kilogram of VSS per hour. I would like to look at this on a daily basis, and I'd like to look at this in relation to SS. I use that approximately 1 kilogram of SS equals 0.8 kilogram VSS for biomass. I'm looking at the rate and I'm saying, well, here I'm gonna go for an average, a daily average. So I'm gonna multiply by 24 hours a day and say, well, since the water is gonna stay in here for approximately 24 hours, and since my outlet requirement is an average, I'm gonna go for an average rate here, and a little bit going closer to the edge. So I could always discuss, should I add a little safety at some point, but now I'm going for that. So 0.9 grams of nitrogen per kilogram VSS per hour. I multiply by 24 hours per day, and I multiply by 0.8 kilogram VSS per kilogram SS. And then I get a rate here. Of 17 grams of nitrogen per kilogram SS per day. So my mass of sludge, or you could say, the volume of the denitrification reactor is equal to the mass of nitrogen I have to denitrify divided by the rate and divided by the concentration of biosolids. So the rate was 0.017 kilogram. I could write it in symbols first. And then with numbers, I had 122 kilogram per day and a rate of 0.0717 kilogram nitrogen per kilogram SS per day, and I have 5 kilogram SS per cubic meter in my process tank, the same everywhere in the plant. In the process, the same sludge going around. So 122 divided by 17 divided by 5. So 1435 cubic meter of anoxic process volume. So now I'm practically home. I could just check up on the FM ratio. So an FM ratio for the entire plant, how would that be calculated? Let's see if I've got it. So the FM ratio will be, global FM ratio will be the amount of food at the inlet. I'm looking at the 85 percentile again, and then the total mass of sludge in the system. So the total volume times the concentration of biosolids. So I had my 1000 kilogram, and I have 2720, and I have 1435. Cubic meter and 5 kilograms sludge per cubic meter, giving me 720 plus, and then multiplied by 1000 and divided by 5. So 0.05 kilogram BOD per kilogram SS per day. So I assumed that I was low when I picked my yield constant, and I have found out that that is true. I might even be able to say, well, my yield constant could be slightly smaller, but then again, this yield constant, it depends on a lot of different things. So I have to take care not to be too optimistic about this. That will jeopardize my design. That's it.